Okay, so far we have looked at how we can model sequential logic in Verilog. Now comes a fairly important part of this entire design process, which is understanding the notion of synthesis, right? And before we get into the details of synthesis, we want to sort of understand this notion of something called RTL. Now RTL basically stands for register transfer level, and what we are saying over here is that we would like to describe digital circuits in terms of registers, that are storage elements, right. So we have a bunch of registers and all of them are somehow controlled by a clock. The outputs of those registers essentially correspond to some kind of a state of the system. There are then computations that are performed out here, and those computations result in outputs that then further go into other registers, or potentially even eventually making their way back into the same old registers out here, right. But this basic notion that I have something which is stored in a register, the present state of my system, combined with possibly inputs, performs a computation and results in a new set of registers getting a new set of register values, which either is a different set of registers or could also be the same set of registers getting updated again, right. This is essentially what we refer to as register transfer, right. Every synchronous digital circuit can be thought of as a set of register transfers, right. And it is important that you be able to actually think in terms of what your design is doing at the register transfer level. What that means is you should be able to break whatever design you want down into a set of storage elements where some values are being stored and some computations which work on those values, perform some kind of complex computations and derive new values that are then going to be stored in those storage locations, right. That once you have your design down to that level, now the storage could also be coming from memory, right, it could be from other registers. The computations in general are combinational logic. So once we are able to break our design down clearly into storage elements, variables, values, right, and computations, it means that we can actually express it in a way that can actually be converted into hardware. It also means that we are able to think in terms of what happens at every clock cycle, right. We are actually able to think in terms of, I have certain inputs, they are getting, some computations are happening and this data is getting transferred from one set of registers to another. Until you are able to break your design down into that kind of a register transfer, you don't have a thorough understanding of what you are trying to actually implement. So the most important part of this entire course, right, that I would like to stress upon again and again is, it's not about can you write syntactically correct Verilog code which will pass a simulation even, right. That is for the most part irrelevant. You may or you may not. What matters is, does the code you correspond to actually or that you write correspond to an actual piece of hardware. And for that you should be able to explain it in terms of a register transfer. You should be able to say what are the storage values that need to be constrained or contained within the system, what are the computations being performed, and how does this register transfer actually occur in practice. Okay. So register transfer is a very important concept. It is also a slightly tricky concept because there are lots of instances where you just write Verilog code and people sort of tend to think of it as, okay, this is the RTL. People almost tend to use the word RTL interchangeably with Verilog. That's not the case. There is a lot of Verilog you can write which is not RTL. Okay. So in terms of RTL, you need to think in terms of storage elements, the data transfers and the logic operations, the computations that are being performed on the data, right. And the focus is on the data flow. How is the data actually being processed and flowing between different sets of registers, not on the individual gates. And the whole point is that you don't need to worry about how these individual computational elements are implemented. That is the part where the compiler can help you. What you need to take care of is making sure that your logical flow is correct. This represents the most general form of synchronous digital design, and by synchronous digital design what I mean is a digital circuit where operations happen on clock edges, or rather where updates to state happen on clock edges. So This is an example of Verilog code which is syntactically correct but is not what we would call RTL, it is not register transfer level. Now let us try and understand why, right. It has an always block that seems okay, I mean we do not know whether always is RTL or not, but my claim is that yes, RTL should still be synthesizable, right, or rather RTL should be able to make use of always blocks. One of the issues that we face is there is suddenly one #2 out here, right, which seems to indicate a delay of 2 nanoseconds and then saying y is equal to a plus b. And one of the issues over here is this is not synthesizable. It turns out that if I want to have a signal being delayed by 2 nanoseconds inside a digital hardware, it doesn't really make sense to talk about exactly delaying by 2 nanoseconds. I can talk about delaying by 1 clock cycle. That's easy, I just put it through a register and the output is delayed by 1 clock cycle because only at the edge of next edge of the clock will the output update. But to say that wait for 2 nanoseconds and do something else sort of requires an understanding of what nanoseconds level time is, which does not exist inside a circuit, right. So a #2 is basically not synthesizable. I cannot get a precise 2 nanosecond delay in hardware. Or to be more accurate, if you do want a precise 2 nanosecond delay, that becomes a fairly complicated piece of analog circuitry where you need to do a very careful matching of different lengths and so on in order to get that kind of delay, right, and it's definitely not what you intend if you think that you are trying to design digital logic. Now the second part of it is we have a for loop, right, and the for loop over here basically says I have a for loop just like in C or any other language. I have a variable, I am initializing it, I have a termination condition, I have I is equal to I plus 1 and I am sort of doing Z of I is equal to Y star 2, right. So this suddenly starts to become a much more complex set of operations. First of all, how do I even do update of multiple different things all at once? It's not very clear, right. So on the face of it, logic written like this is in general not what we would call RTL. It doesn't qualify as proper register transfer level. We don't have clarity on what our registers are, on how the computations are to be performed and how to update them. On the other hand, if I have a relatively simple piece of logic like this, right, I essentially say I have a very clear register transfer. I have some A input, another B, which once again are both coming from registers in the first place, although they could come from inputs, external inputs as well, right. Some computation is being performed and the output is being assigned to another result register, okay. It turns out that this is fairly easy to understand. I have a clock edge, I know exactly when the transfer is supposed to take place. I know when A and B can be considered to have proper stable values. I know what kind of computation I can perform with them, in this case an addition, and I know how to get that result into another register, right. Now actually you could have potentially slightly more complex computations here as well and it could still sort of qualify as RTL, provided that you have a simple way of implementing that computation. If for example I do something like A reg multiplied by B reg or something of that sort, and I don't have a simple way of doing a multiplication in a single clock cycle as something that can just be used in order to transfer from one register to another, I would end up having the result that this is actually not something that can be implemented as an RTL piece of logic. What do I mean by that? It means that when I have written code like this, I assume that whatever computation is happening here is something that is happening combinationally within the time period of a single clock cycle and can therefore be used in order to update the output register. So the general structure of RTL, right, is that we have very often we tend to sort of break the computation into two parts. One of them is the actual computation itself, right, where I sort of declare an intermediate variable, right, a wire or something like that to hold the result of my computation, and then I can actually explicitly have a synchronous register update, right, where I just say that sum reg equal to result. What I have done here is I have a combinational block and I have a sequential block, and this sort of corresponds to the diagram that I showed earlier, which basically says I have these registers, I have combinational logic, and I have this output going back into a set of registers, right. In this case, you need to keep in mind that I am actually talking about a bunch of registers out here. So this output may actually go into one of the other registers and not the one that it started from, right. As you can see, A reg, B reg might be two of these registers, and some reg is yet another one of the registers. All that it's saying is the inputs over here came from two of them, something happened and the output finally went back into yet another register out here. So assuming that we have got the handle of how to write RTL, and of course the only way to really understand it is through examples, and we'll be working through many examples as part of the assignments and so on, right. We now need to address another question, which is, okay, the RTL sounds alright, I have a mental picture of what my flip-flops and my logic look like, but do I actually need to create each one of those gates and put them down somewhere and connect them up, or is there some way by which magically all of this can come in place for me? And the answer is, that is where the synthesis flow comes in, right. Synthesis essentially refers to the process by which there is a program, a compiler, right, which takes the Verilog RTL that you have written and converts it into another format. This sounds exactly like what a C compiler does, right. It basically takes your C code, converts it into an intermediate representation, does some kind of optimizations on it, finally generates assembly language and then machine code for you. In this case, what we have is, we have something where I write Verilog code or VHDL, there is a compiler that parses it and creates an intermediate representation. It identifies registers, combinational logic and so on inside this code, does a lot of optimizations, whatever we would have done with Karnaugh maps and various other kinds of Boolean optimizations are automated away in there, right. And finally it maps it into a target technology, meaning that it generates an output which is a set of gates. Unlike a C compiler which generates an output which is assembly or machine language code, a Verilog compiler would generate a set of gates. But otherwise there is actually a lot more similarity between a C compiler and a Verilog compiler than there are differences, right. It is more in terms of what is the final target code that is being generated. The outputs that come out of a synthesis process are what we call a gate level netlist. So the gate level, what do I mean by that? The gates are just the AND, OR, XOR type of gates, or in the case of an FPGA they could be lookup tables, right, with the appropriate configuration to say, okay, what should the lookup table behave like. The netlist says that I have the connections of each of these gates. I have named instances of many different gates and I have wires that are connecting all of those gates together in the appropriate way. The synthesis also generates what's called a resource utilization report, which basically tells you how many gates of different types are required in order to implement the logic that you want, right. And it will also give you a set of warning or error messages, right. And these warning messages are things that you should generally learn to pay attention to, right. Error messages of course would hopefully make you just stop and you have to go back and fix it, but there can be scenarios where you get warnings, right, similar to compiler warnings in a C program, but very often the warnings that you get in synthesis are more dramatic. They actually can lead to scenarios where you think things are working properly but they are not going to work when you finally put it on hardware. As with any other kind of programming, the idea of garbage in, garbage out always holds, right. If you have not written code keeping the principles of RTL based design in mind, right, it is almost certain that you will get syntactically correct Verilog code which may even pass your simulations, but which will not give you a netlist that actually does what you want. So please keep that in mind. I will be repeating it multiple times throughout the course. Your goal is not just to write Verilog, it is to design hardware. So you need to think about what your hardware should look like and then figure out how to write the code that will give you the design that you want.